I'm Ivory.
I'm Diego.
I'm Paula.
I'm Anaya.
I'm Tyler.
And I'm Jacob.
And
We're Leaning Tower of Pisa.
So for our initial design, we built the structure with the intention of maintaining a flexible and strong support system. With flexibility, this would allow the building to absorb the shear forces enacted upon it while also keeping the structure intact. If the structure were to not be flexible, the rigidity would prevent the building from shaking and moving alongside the earthquake, causing stress to be placed upon it and cause damage to the structure. Essentially, rigidity throughout the structure would cause it to crack under the pressure of not being able to move alongside the earthquake and unable to absorb the forces acting upon it. For the first aspect of our structure, we decided to include base isolators because we wanted a structure to be flexible and strong. With base isolators, it will be able to combat the shear forces since base isolators are designed to mimic the foundation desired, that being bedrock. We want bedrock because it diminishes amplification of the motion of the earthquake, thereby creating a less intense shear force upon the structure. Base isolators are also separate from the foundation of the building and allow the foundation to absorb the impact of the earthquake without the actual structure receiving much of the impact.
We also decided to use cross bracing within our structure because it absorbs the shear forces that compresses and tenses the structure. As a distributing member, the cross bracing takes the seismic movement and disperses this force to the foundation.
In addition to using the base isolators, we decided to use a steel slab foundation using the garden wires as the steel. By using this, we would mitigate the impact of the ground motion, allowing the building to ride out the shear force. It was also an optimal choice considering that the slab foundation is used when conditions are uncertain and because the guest speaker would move it at different speeds, it would be effective, therefore allowing the building to have a better chance of survival.
We use beams as a way to really just hold everything together, and we use columns as a way to support the weight of the upper floors.
Because the way base isolators move is that it's made out of rubber, so they can be flexible. Okay, so let's do that.
Build on.
Now I think now it's
Wait, now shut the bus? No.
Landscape only.
I was thinking maybe something like that, and then we could build like rails around it so it doesn't fall off.
Yeah.
Or like leave some room of it so it can
Scholars.
and then like after start building on top. And we'll glue
Yo,
this,
I got a landscape.
You want it to be landscape?
glue these
Yeah.
pieces on the floor. On the
No.
For both sides. Oh, we're not gonna do it on this side? What do you mean? Like, you're saying on this side and like this side.
Yeah, I was thinking just the sides, but we could do it all the way around too, and maybe like limit some at the top. What do you think?
Yeah.
Extra reinforcements. Maybe we should leave it like that so that I can sway a bit, but add some right here. 216.5 grams.
216, 217 grams. Okay. Okay, here we go. Okay. All right. You guys think this is going to be stiff or flexible?
Flexible.
Okay, here we go. Oh.
We failed.
Foundation failure.
Yeah.
It was pretty stiff.
Shear force is caused by forces that pull in an object in opposite directions, parallel to the surface. Shear force is produced through the secondary S waves that propagate from the earthquake. Resonance occurs when the natural frequency of the building matches up with the natural frequency of the foundation shaking. When this occurs, the wave forces compound upon each other, creating a much stronger shear force than you would have to deal with otherwise. To avoid the compound shaking of resonance, you need to make sure the frequency of the foundation shaking doesn't match the natural frequency of the building. Stiffer and shorter buildings have a higher frequency, while taller, more flexible buildings have lower frequency. Our building was moderately stiff and moderately tall, leading to a medium frequency. This checks out since our building experienced the most swaying motion when it moved under a medium frequency. In the Hearst mining building, many base isolators are used in order to stop the building from moving at all, as long as the shear force and displacement isn't too great. For the specific test we were doing though, base isolators can't really do their function correctly. We moved the bottom plane at an incredible distance during our test, one that is not even close to what actually happens during earthquakes. The huge distance of displacement compared to our small base isolator means that they couldn't really isolate the base. If we were to shake the table with less displacement and maybe multiple directions, then the base isolators would have assumed their proper function.
Our building was attributed to a foundation failure because the glue came undone on our makeshift base isolators with the side-to-side forces of the structure, also known as shear forces. The sway of the building structure caused the glue to slowly rip and lose its grip until the building completely became separate from the base isolators, causing our failure. And even if our isolators worked, it wouldn't have been helpful because they were not properly attached to the structure. Though the base isolators were not properly glued to our structure, we can see the base isolators are still attached to the foundation.
Additionally, the marshmallows dried up and made our base isolators more rigid, thereby causing the base isolators to lose flexibility. Without the ability to move and absorb the shear forces, there was more stress placed on the base isolators, which caused the structure to fail. We found that there was a failure in the foundation as the rest of the structure remained more steady and fully intact during the shaking. The construction of the building was not the issue, it was more so the attachment and the functionality of the base isolators themselves. The force of the fall due to the foundation caused a collapse in our structure.
Upon further inspection of the video, we found what may be the principal cause of failure in the structure. We looked really closely at the foundation of the structure during the final oscillations and found that the one whole side of the structure was being lifted up. This up and down motion was a total predicament to us since we'd expect the only major motion to be side to side from the shake table. After even further inquiry, we discovered that this up and down motion on one side of the structure was actually caused by bending and elastic forces. Since the up and down movement was experienced only by the side with one base isolator, we deduced that the bending must be due to specific orientation and construction of that side. After thinking about it more, everything makes complete sense. The columns on the side with one base isolator are conveying all of the load to the points far outside the structure's connection to the ground. This creates a situation where the base isolator is pushing against the middle of the spaghetti, while the columns are pushing down on the ends. This scenario is a classic example of bending, and that large bending force is exactly what caused our structure to fall down on one side.
The purpose of columns is to convey the weight of the structure down to the ground. Basically, they are vertical load-bearing elements, beams and horizontal members that distribute weight from floor slabs into the vertical columns. They also distribute horizontal forces in the building and keep everything connected. Since there is no floor weight in our building, the beams acted mainly as connected and distributed horizontal tissue. The shear forces caused by up and down movement in the structure were sufficiently braced and dispersed by the beams, allowing for our actual structure to be totally intact. Up and down normal forces were not accounted for, however, as there was no direct way for the forces to go from the column to the ground. The columns not being attached directly to the base isolators allowed for up and down movement to cause an elastic rebound effect, leading to the eventual failure of our structure. We ignored basic structural ideas and forgot to convey all the load from the columns to the ground, instead suspending the columns under a large low wooden free space, putting immense pressure and unforeseen reaction onto the entirety of the structure. Another result of our triangular-shaped base isolators is that our building reacts differently depending on the directions of the forces put upon it. Think about it geometrically. Pushing on a triangle from its base will cause different reactions than pushing it from its side. In our case, we push the triangle from its base, causing a stronger swaying motion than if we were to push it from the side. The structure remained intact, so all we can say is that the cross bracing did, in fact, do its job in protecting against shear forces. There was little lateral movement of the actual structure. Most of the movement came from the angular swaying that resulted from the elastic rebound discussed earlier.
The up and down movement must have been due to the elastic reaction of the spaghetti to the bending force. We were unaware of this elastic oscillation before the experiment since it was locked in a state of equilibrium. It was the disruption caused by the swaying of the structure that must have exposed this otherwise unnoticed reaction. So why does this matter? Well, as it turns out, glue is extremely weak in tension in comparison to shear, and up and down motion would have exposed the glue to tensional forces, thereby attacking the weak point of our connection and exposing it to forces we did not build for. What we said before can still hold true, but is all deemed useless in consideration when the real mode of failure was something completely different, something unfixable through ordinary additions of more glue or more marshmallow. What we needed is a complete revamp of our structure, one where bending was avoided and rigidity is reinforced. By focusing entirely on our structure's resistance to earthquakes, we ignored basic structural ideas and forgot to convey all of the load from the columns to the ground. What we should have done is make sure the columns were connected to the ground, either by making the base isolators match the columns of the structure or by making the columns match the base isolators. What was essential is that they come together at the same points. While we could go on and on about other aspects of the structure, we will never truly know how they would have performed, as this one faulty aspect of our design would have caused failure regardless of whatever else we did.